Hi everybody, thanks for the great introduction, Rudy. Actually, we haven't shared a stage together since my PhD defense, so I'm hoping that this talk isn't quite as stressful as that one. Okay, so let's get started. Well, first off, I had a few words about myself, which I will now skip because Rudy gave such a nice introduction. So, as he said, I develop DSP for instruments and effects at Native Instruments. A little bit about my company, Native Instruments. So we're one of the largest music tech companies in Europe. We've been around since 1996, and we have offices now in Berlin, in LA, London, Shenzhen, and Tokyo. And we have about 600 people now. I think it might even be up to 700. It's a lot of people, and growing all the time. Only a few of those people work on DSP, though, which is, I guess, just the way it is. You need all those other people supporting getting things to market, all the other things that a company requires to operate. So tiny bit of history about Native Instruments. We started out with a program called Generator back in the late 90s. It was one of the first software modular synths. Soon after that, we came out with a package called Transformator, which was kind of an equivalent of Generator, but for manipulating samples. And then a little while after that, they were merged together to make Reactor, which is a package for doing both and is still kind of one of our core things until this day. Yeah, some other things about Native. So we're one of the first companies releasing VST instruments, not the first, but one of the first, and also digital DJ software. And we've been heavily involved in the last years with pushing kind of integration between hardware and software solutions. Okay, so enough about that. Let's get on to the main topic of the talk. So to kind of explain why I'm giving this talk, I wanted to say a little bit about what a DSP developer at Native Instruments does. So you can kind of divide our work into three main categories. So to start off with, we do kind of low-level research on DSP algorithms, which is the very DAFx-y kind of stuff, things that you're all kind of familiar with, I guess. Then we take those algorithms and we need to turn them into like engaging devices for a user to take and make music from. This is basically what I'm going to talk about in this talk. And then finally, we work on implementing this stuff efficiently in C++ and software development stuff, which I won't talk about here. Yeah. So first off, before I get into the talk in general, I want to say, what's my definition of an instrument, at least for the purpose of this talk? Basically, I'm defining an instrument as being any device, like physical or virtual, that you can use to generate or modify sound for creative use. So that could be a guitar pedal, it could be a piece of software, it could be a synthesizer, it could be a modular synth, it could be a rack effects processor. Anything that you would use creatively to do something with sound, I'm classing as an instrument. So, yeah, most of us in this room, being DAFx people, we're used to developing algorithms that are intended for creative use, at least eventually. We might only present a small part of it at this conference, but that is usually the end goal. So I would say broadly, like the things that we're talking about at DAFx kind of fall into this definition of instruments. However, when you're writing a paper, you tend to be aiming at a very specific set of criteria, like the things that academia wants to see in order for something to seem novel and for something to seem like a good contribution. Usually that's about technical novelty, so introducing new methods, or it's about quantitative results. So like you've improved the signal-to-noise ratio of some process, it's better than it was before, you can show some definite improvement. Now the thing is, when you start making this stuff not for publication, but for use by people, then these factors are not that important anymore. You've got to start worrying about lots and lots of other factors. And these are things that generally we haven't talked about at DAFx, and actually they make up the majority of the work of taking an algorithm, getting it out into the world for people to use. So yeah, today basically what I wanted to do was kind of say something about how we can bridge this gap and my experiences of making this transition from the technical to the artistic tool. So a little bit of a disclaimer first. The first one is that what I'm saying today is not meant to be universal, really. This is just my personal experience and the personal kind of rules for myself that I've come up with Other people, I'm sure, have different approaches that are equally valid. This is just, my perspective on it. Also, of course, like Rudy has mentioned, I'm in the end, a technical guy, a scientist or an engineer, however you want to put it. So I'm not a trained designer, although I now do quite a lot of design work. So I'm really not talking in the language of academic design. I'm talking in my own language, which I hope is easy to understand. But, don't read what I'm saying from the perspective of the academic design literature, because this is not something that I'm particularly familiar with. So, yeah. OK, so if we're designing an instrument, like a device for creative use, then what are we aiming for? What are the goals of this process? Well, generally, I would say that we want a device that can inspire the user. Like, this is obvious, right? You want to have something that somebody can take, and it will not just fulfill the task that they want to fulfill with a thing. You want it to suggest new kind of things to the person, like take them in new directions, inspire them, basically. You want to give them a very musically interesting kind of sonic space to explore, like without lots of dead ends that don't do anything interesting. You want to provide some kind of element of collaboration with the user, so surprises, happy accidents, like things you might not expect, but that are positive in a creative sense. And then finally, and I guess in a way most importantly, you want to leave the best possible results on record. So people generally at the end of a creative process will have some kind of, recording or video or something, a hard copy of what they've done. And when you're making a device for people to use to make this kind of thing, then it's I feel like it's important for us to allow these people to, leave the best possible recording possible of what they were trying to do. So, yeah, sound quality is a big goal as well. So, general principles for this process. Before I get into the specifics. So first off, I always think that it's really important to find a perspective for the thing that you're designing. So something that's unique about what you're doing, and then really concentrate on that. Give the thing that you're making an identity. Nobody wants to, well, most people are not interested in yet another compressor that does exactly the same thing as every other compressor on the market. Like, how would you tell which one to use then? Like, you want to pick a thing, and you want to really bring out that thing to make your device unique. Another general principle, so parameterization is incredibly important. So the number of parameters, their ranges, how they're tuned, incredibly important. I'm going to talk about that more later. Focus. This is kind of related to the first principle. So don't try and be all things to all people. It's better to do one thing really, really, really well than like 10 things in a mediocre way. I mean, that should be self-evident, I think, but still, I don't know, it's a trap that it's easy to fall into. Like, if you're designing something, you obviously want to give people more possibilities and more possibilities and more possibilities, but then you don't step back to think, hey, are these all worthwhile? Maybe I should just do the one possibility and then make it really great. Yeah, so another important thing, and this is true of developing any kind of product in any industry, I think. Like, you really need to think about what the user really wants subconsciously. So not what they say they want, but what you've got to unpick what people say they want and try and work out from that what they actually want. This comes up so often in my day-to-day work, actually. Generally, you get feedback from people, whether they're beta testers or sound designers or customers, and it's always in the form of feature requests. It's like, I would like this extra knob that does this thing. And the thing is, like, this is often, you can't basically implement all of these feature requests, because you'll end up with a mess. Like, if you give everybody a knob to do the one thing that they want to do, then you end up with a giant device that basically satisfies nobody. So it's really important to kind of think about what people are saying, like why they say they might want this feature, like unpick what they're trying to achieve by doing this, and then maybe work out a way of doing it without just adding more capabilities. Like, maybe it's just a change in parameterization that you need to do. Yeah, so the final general principle is never sacrifice sound quality. This is basically towards the same goal that I stated on the last slide. Like, sound quality is of the utmost importance. This is the thing that's lasting about what you're making. Like, this is what goes on record, so don't sacrifice it. Unless you're doing it intentionally, then it's fine. Yeah, so this is what I want to talk about first, like kind of general topics around sound quality and also some kind of common DSP pitfalls that people tend to fall into if they're new to kind of making stuff for people to use rather than for a paper. So, yeah, some general guidelines about sound quality. So the first thing, and actually I would say the most important thing, is that you need to learn to listen analytically. Like, the process of developing something for a user will go so much more quickly if you can listen to the output of your device and you can make the connection, at least reasonably quickly, between any kind of qualities that you're hearing, whether positive or negative, and what's causing them. If you know what's causing a particular sound and you know how to change it, then it makes this iteration process and this improvement process much, much quicker. Like, this may sound kind of basic, but I think it's very easy to go into a problem and just like reach around in the dark and not understand what you're changing and how it affects the end result. You're just kind of changing things blindly and hoping that it has the effect that you would hope for. This is bad. Like, if you want to be efficient, then you really need to spend time kind of listening to the way different things alter sound and generate some kind of feeling for how these things are related. Yeah, so another kind of pillar of good sound quality, that is that basically if you're offering something as a parameter, so whether this is a knob on a hardware device or a knob on a GUI or like something that's automatable in a door, like basically if you're giving people the opportunity to change something in real time, you better make sure that that thing can be played. Like, they should be able to grab that knob, move it around, and it should sound good. It shouldn't mess up the sound, it shouldn't cause glitching, blah, blah, blah. This is another one that it's surprisingly easy to violate because often you have to jump through some hoops in order to enable this, but in my opinion, it's really important. Yeah, next pillar of sound quality. So I think you need to try and strive to always achieve the best version of what you're trying to do. So it's okay to have aliasing, it's okay to have distortion, but they should be there because you want them to be there. They shouldn't be there because you didn't refine the method enough and you couldn't find a way to eliminate them. I think it's best to start from a baseline of absolute cleanness if possible and then add in the elements that you want on top of that or bring them back in rather than just dealing with what you've got. I mean, that way it's easier to arrive at something that you want. Yeah, and the final kind of pillar of sound quality is that, I don't know, I was inspired by, I don't know how many of you people follow cycling, but there was this extremely kind of successful cycling team, Team Sky, like 5-10 years ago. I think they're a bit disgraced now. There was some doping allegations or whatever, but they had a philosophy that nevertheless was pretty good, I thought, which was that if you make lots and lots of tiny improvements to your performance in all kinds of unrelated areas, then when you add them all up, even though they were small improvements, you've got like a big return. And I think the same is true of sound quality. Like, it doesn't matter how small an improvement is. If you make 20 of those small improvements all throughout your device, then the end result is going to be something that sounds much better. So yeah, basically the lesson is don't think that things are too minor. They're probably not. They'll add up into something big in the end. So common DSP pitfalls. The first one, actually a couple of these were covered really nicely by Dave in his previous talk already, so I won't dwell on it too much, but I'll still say something. So the first thing to remember, and something that's only really become that's kind of entered the music DSP literature recently is music is not an LTI thing. Music is by its very nature dynamic. It moves, it changes. So basing the structures that we use for music DSP on traditional DSP literature, which is massively based around the LTI assumption, tends to lead down bad paths in my experience. So a really kind of clear example of this is direct form structures. So Dave actually already described a nice way of making direct form structures behave better in response to time-varying parameters. But still, in general, I would say if you can avoid using direct forms, it's best if you do. They tend to have problems with stability. They're not great for things that move around. There's some wonderful alternatives that you can use instead that will allow you to do exactly the same things, but just you have to start from a different viewpoint. So I would recommend using, basically starting from discrete time prototypes. So filters that you would design in the analog domain, and then using that as your prototype for the digital filter that you want to build, but not in the traditional way. So not starting from a Butterworth impulse frequency response or a Chebyshev or whatever, but from an actual topology, from a structure. So two particularly nice ones that I use a lot in my work personally are the state variable filter, which you can see here, and the transposed Sallen-Key filter, which is a Sallen-Key filter run backwards. So these are continuous time block diagrams. If you discretize them very, very simply using, even in the linear form with trapezoidal integration or the bilinear transform or whatever you want to call it, then you end up with incredibly well-behaved digital filters that you can basically implement any second-order transfer function that you want to with, and they behave so much better than direct forms. So like already, you use these structures, you'll remove a lot of problems. So that was the first common pitfall. Another big thing is interpolation. So I don't know how many times in my life I've opened up a reverb plugin, like turned like a size knob or something, and the result is that you get this huge kind of crash of, I don't know, noise from lack of delay line interpolation. I think generally this is something that you don't want to do. You want to use interpolation in cases where things change dynamically. I mean, this is obvious again, but like it's surprising how many people overlook this. But from the opposite angle, I would say don't use fractional delays when you don't need to. Basically, any kind of interpolation or fractional delay algorithm will introduce some filtering into the signal. So if you've got a delay that is static most of the time, even if it moves sometimes, then don't have it sitting there on a fractional delay because you'll be filtering. Like an inside a reverb or a delay line or something like this, that will completely muck up your sound. It's often better, in fact, even if you're using an interpolated delay line to move between values, maybe just quantize your final value to a sample boundary so that you've got perfect quality in the static case. You accept kind of some little bit of jitter in timing then, but only less than a sample, and then you don't have any filtering. So then you can, basically use fractional delay when you need it, when things move, don't when you don't. Another thing that it's important to consider is that, so like I just said, interpolation is important, and of course, high quality interpolation. So higher order interpolators are often a good thing to use, but don't always assume that they're the best thing. When you start moving around, for example, delay line lengths, you're going to be hitting a lot of different fractional delays. The filtering that this introduces into the signal will then vary, and what you suddenly have is basically like an amplitude modulation of higher harmonics, which can introduce aliasing and all kinds of crap into your signal. So sometimes you might want to design an interpolator, rather than having a great frequency response, it might have a bad frequency response that doesn't vary that much when you move it around. And this will maybe, in the end, give you better results. So just to illustrate this kind of modulation problem, I just had a quick plot in MATLAB. Let's make it a little bit bigger. So this is basically just plotting the frequency response of a Catmull-Rom interpolator for a variety of different fractional delays. And you can see by how much the frequency response varies, and therefore how much a input component in that frequency range would be amplitude modulated. So let's just run it. So we can see it starts off not much, but then gets a lot more, like you end up with many dB of attenuation. So if you've got a signal going in at, I don't know, say if you're working at 44.1 at 20K or close to the Nyquist, or even 15K, then that signal is going to be amplitude modulated quite a lot. You're going to get a lot of stuff generated. It's not good. So yeah, avoid that. The next common pitfall. So aliasing. Obviously, this is like a incredibly common topic at DAFx. Like, we've come up with many ways of avoiding aliasing in all kinds of different situations. So my advice here really is just use them. Like, basically pretty much anything that you can do now that would introduce aliasing in your signal, whether that be some kind of wave shaping, introducing discontinuities, modulation, whatever, there is now a pretty well developed method for suppressing this aliasing. So, you know, please use them if you can, because it will pay off. Like, you may think that the aliasing from one particular operation is not significant, but like I said before, like, these things add up. If you have a little bit of aliasing coming from many different places, then it can really drastically affect the sound and the behavior of a larger structure. So, you know, if you have these methods available to you, then use them. Another thing, like, strongly related to the aliasing question is control signals and smoothing of control signals. So generally, you will have controls coming in from somewhere in your device, so like maybe from knobs in a hardware device or from the VST interface, wherever. And often they do not provide like a nice, clean stream of changes. Probably doesn't happen at audio rate, and it's probably quite steppy. This is bad, obviously. So any discontinuity in a control signal, whether it comes from bad data or running it at a lower rate or whatever, this is audible. Like, any stepped change in a parameter will introduce a discontinuity somewhere in your system. This will generate aliasing or a click or a pop. It's bad, basically. So it's very, very important always to think about how your control signals are changing and make sure that they're smooth. Okay, so another thing that Dave talked about quite a lot. Delay-free loops. I won't dwell on this much, but I will just say that there's been a lot of preoccupation with delay-free loops over the last, 30 years of DSP literature. People have worried about them an awful lot. I'm not entirely sure why. I think there must be a historical reason why this was such a big topic, but it turns out we know now that they're really not a problem. Division exists, basically. This is the thing. So you can see a little block diagram in the bottom here of a very, very trivial kind of signal processing system. Okay, it doesn't have any states, but it represents some signal flow. And you have the algebraic representation on the other side here. And you can see that this delay-free loop is, of course, just an implicit algebraic relationship. You rearrange the equation, boom, you don't have a problem anymore. Of course, things are a little bit more difficult in the nonlinear case, and then you need to use methods like Dave was talking about. But still, they work very well. It's very rarely the best solution to look at a delay-free loop and say, uh-oh, this isn't good, let me stick a delay in there just to make it explicit. That's very, very rarely the best solution. Yeah, I won't dwell on that anymore. Yeah, and the final big kind of DSP pitfall, from my perspective, is that basically the question of gain staging and loudness. So it's very, very easy to make an algorithm that produces a very, very different level of signal than the one that you put into it. So either much, much louder or much, much quieter. Like, even professional devices often do this. I would say, at least from my perspective, that this is a bad thing. Like, generally, a processing device, unless it's like a maximizer or something that you really want to pump up the perceived loudness of a signal, basically you don't want to change the loudness of what you put in. Like, generally, at least an effects processing device is about changing the character of something rather than making it louder. So it's really, really important to identify any kind of structures within the thing that you're designing that might cause a loudness boost. So common things are feedbacks, strong resonance in filters, like long tails on reverbs, like driving a distortion hard, things like this. It's really important to identify these, kind of characterize how they're affecting the overall loudness at the output of the system, and then compensate for it so that you have a smooth kind of experience when you're changing these parameters, so that you don't just change something and then suddenly it's clipping all the rest of your system. That's something you really want to avoid. I will say there's a caveat there, though, so you don't want to make the compensation too perfect. Sometimes if you compensate for these things exactly, then you suck the life out of the sound. So for example, if you have a resonant filter and you normalize the output so that the resonant peak is always at 0 dB or something, then the experience of turning up the resonance just sounds like you're losing, like you just have a resonant peak, you have nothing else left. So generally you want to reach this happy medium point where you don't get an insane kind of loudness boost, but you're also not like sucking the life out of the sound. And this can be hard to do sometimes. So I've got a little live demo in Reactor here now to demonstrate this kind of loudness equalization in situ. So I have a little system here. So for some of these demos, basically I took some of our, basically one of our products. So this is Blocks. It's our version of a modular synth. And then I started removing some of the nice stuff we'd done to make the stuff behave well, so that I could demonstrate like why we'd done this stuff. So this particular case, it's about the loudness. So we have an oscillator with a sawtooth wave just set up going into a comb filter. So at the moment I have there's a compensation on the output for the loudness that depends on the feedback, on this damping parameter, which is like a low-pass filter in the feedback loop, and also the frequency. At the moment it's turned off, so if I turn it on, we'll see that we get kind of wildly varying output levels. So I can move this around. So you see pretty quiet with no feedback. I suddenly turn up the feedback, it gets loud. Actually, I hope you guys don't have a compressor on the output of the system, otherwise this is going to muck up my... Okay. You might have to take my word for it. But so I can connect this cable here, and we have our loudness compensation switch back in, which in this case is basically just is based on the peak gain of the peaks of the comb filter, and also some extra linear kind of normalization for the frequency and for the damping. So we can turn this back on, and we can see that now you have a much smoother experience. Now it's really just the timbre changing rather than the loudness, which is generally desirable. That's what you want to do. So do it. Okay, so that's the end of my small section on sound quality. The next big topic, okay, we're halfway through, is parameterization. So this is obviously the other kind of huge topic that you need to tackle if you want to create an interesting device for the end user. And it also has really a lot of pitfalls. So something that I take as a tenet is generally that, like I said before, every parameter should be playable. Like it should feel like an instrument when you manipulate this device. Like you should be able to grab something and it should do something cool, rather than it feeling kind of bad or you've got to search around for the right spot. So yeah, I always try and, well, in fact, you don't just need to think about what it feels like to be a user and turn a knob. You can just set it up for your device. Like have the thing running, have something controlling it, like turn the knob. Like try and think from the perspective of the user. Like, am I turning for a little while and nothing happens, and then something happens really fast and then nothing happens again? Avoid it. This is quite easy to do in most cases as well. So one big thing is that, I mean, and this is super obvious, I would hope that most people would spot this. If you have any kind of like frequency control, generally you don't want it to be like a linear thing. Like you don't want to have just a knob that goes from 0 to 20 kilohertz, like linearly, because you'll have like a really interesting range in the first 10% of the knob, and then like a whole load of nothing in the rest. So use a logarithmic range. This is also true for delay times often. Like often there's a whole range of interesting stuff happening in the low end of the scale, and then further up is a whole lot of stuff that's really similar. So, you know, expand that range where the interesting stuff is happening, and then compress the range where things aren't happening. This is pretty easy for stuff like frequencies, because you can just make it logarithmic. If you have something else like a more abstract parameter, then you can do like maybe polynomial scaling of your parameter. So that's easy to do for like if you need higher resolution in one end of the scale, you can just use a squared function or a square root or whatever. But then if you want to kind of provide more resolution in the middle of the scale, then you can, for example, do a cubic. Like you can place a point within the middle of your range that has like a lower derivative and therefore a higher resolution, and then put that directly on the spot that you think is interesting, and then you'll have a much nicer experience for the user. Like it will zoom in on the cool part, and they'll be able to find interesting stuff much more easily. So again, I have a small demo from blocks of this. Again, a really, really simple usage case. So an oscillator again, going into a state variable filter. So first off, I'm going to demo, maybe this is even too trivial. I'm going to demo a linear frequency control versus a logarithmic one. So filter, linear frequency control. I've got half of it doing very little. Then, wow, okay, I get to the bottom range, and now I can't hit anything in that low range at all, basically. It's not possible. If I switch this over to be pitch scaled, now I have all this usable range. So much easier to find what I want. Simple, but very important. I can also demonstrate the tuning for resonance in this case as well. So, sorry, I've got to find my way back in the structure. It's dangerous doing this stuff live. Where is the resonance? Yeah, here. So, if I make the resonance control a linear thing, like this, you will hear that like 50% of the knob, I don't have much of an audible change in what's going on. Then at the end, I get some nice kind of close to self-oscillation behavior, but I can't really tune it very finely. It's difficult. If I make the controller curve like a square root instead, I already have a much nicer behavior. So you can see even in this first half of the knob, I've got a nice range of stuff going on. And then around the self-oscillation region, I've got a lot more possibilities. So really stupidly simple demo, but you can already see how making these simple changes makes something much more usable. Okay, the next point for parameterization. This is basically like choose your parameters carefully. It really sucks as a user to have like a wall of knobs in front of you, unless, I don't know, actually, maybe for some people this is inspiring, but I tend to find that most people don't like this because it gives you this huge, huge kind of parameter space and no idea about how you're going to feel yourself like around within this space, especially if these parameters are like technical parameters and you don't necessarily fully understand the workings of the system. It's really, really much better to have less parameters, make them more meaningful, and especially like group them nicely on the interface, for example, tie them together with some kind of visualization, make it really obvious what everything is doing, give it a semantic meaning or a clear perceptual meaning. Yeah, so this is basically what I'm saying here. So, I mean, and I really should reiterate this. I think the majority of people who use musical devices will not understand the full workings of what's going on inside. They'll have maybe some kind of idea of what is going on, but it won't be like on the level of the person who's made it. So you should never forget this. Like you should never assume that the person knows what your frequency number 1 or your frequency number 2 is actually doing. You need to group that stuff together maybe, give it an appropriate name that characterizes what it's doing to the sound semantically, and then, you know, guide them around the space basically. I would say that, okay, so I'm saying that you should reduce the parameter set, but this doesn't mean that the parameters should be simple. Like they can they can take you on a very complex path through the sonic space, but as long as, you know, you've thought about this path and made it make sense to the user, then this makes it a lot easier to work with. Okay, yeah, a little case study here. So choruses, one of the most basic audio effects probably, but a surprisingly tricky one when it comes to parameterization. So choruses in the old analog days were generally done with a modulated bucket brigade chip. The problem with this is, well, I mean, if you think about the defining element of a chorus, it's basically like you have your input sound and then you have another copy of the sound, and that copy has some kind of pitch contour, so it has some kind of pitch change over time. You combine this with your original version and it sounds like you have more than one voice playing. Like that's what a chorus is for, right? The trouble is, with this kind of basic BBD setup, so you have a BBD running at a certain clock rate and then maybe an LFO modulating the clock rate, you have this really horrible complex interdependence between the parameters when you're thinking about the pitch contour. So actually you can write down a differential equation for what the pitch at the output of a BBD is, and it's a nonlinear delay differential equation. It's super weird, like the solution is it doesn't turn out the way that you would expect it to at all. You can get all kinds of weird effects happening. So for example, if you turn the delay time to low, like the initial delay time or the initial clock speed, then modulate the time with a triangular LFO, you can actually get a pitch contour out of the system which looks like, I don't know, some kind of trapezoid. So it'll ramp up for a while and then it'll be clipped and then it will ramp down. You wouldn't expect this at all. Like if you then increase the delay time, then it can turn into something that's more like a triangle. Also, the amount of chorusing is dependent on both the rate of the LFO and like how much it's modulating. Basically, it's a horrible kind of parameter space for the user. Like they have 3 interrelated controls and they only really care about manipulating 1, maybe 2 things. So this was a big challenge, I guess, for guys designing choruses back in the day. And it's very telling, I think, that in some of the classic chorus units, the solution was basically to not expose this to the user at all. It's just a bunch of buttons that correspond to preset rates and modulation amounts and delays, and they're tuned carefully to produce a nice sound. Like you don't offer that possibility to the user at all. You just say, this is a nice thing, or this is a nice thing, or this is a nice thing. That's all you've got. Of course, there are units as well that let you tune the parameters, but I think probably they are generally not thought of as well as the devices that work with the buttons. Like if you ask people what their favorite chorus is, then they're more likely to say the Juno chorus or the Dimension D than they are, I don't know, what's a good example? Maybe like the Electro-Harmonic small clone, which has a rate knob. Like that's harder to work with. It doesn't sound as good. So, I mean, this is an example of a situation where you really want to reduce the parameter set and make it really clear in order for the user to get the experience that they want. So in the digital case, this isn't quite so difficult. Generally, a digital chorus is an interpolated delay line with its output point modulated by an LFO. So in this case, though, there is still some subtlety. So the pitch change is related to the derivative of the delay time, so how quickly the delay time is changing. Yet, if you look at most basic chorus plugins or pedals or whatever, then still they just offer basically like an LFO, amplitude control, and a rate control. And you can turn up your amplitude control, get the amount of chorusing or amount of pitch change that you want. Then you change the rate control, and it changes completely. Like you turn it up, you get more pitch change. Like it sucks. Like it's really hard to get the result that you want because these parameters are dependent in an unhelpful way. In this case, there's a really easy solution. You just make the LFO amplitude scale on frequency as well as the control, so that basically you then have decoupled controls for the change over time of the pitch and also the amount of pitch change. So this is a really simple example, but it's basically I'm saying that like it's always important to even just consider these simple things. Like it may seem like a tiny change. You may not even have to do much, but it can make the usability of the device vastly better. So I have a really quick demo again of the difference between this normalization in the chorus or not. So, same sawtooth. I'm using it for all the demos. I hope you don't get bored of it. I have a really simple chorus set up on the output that's basically just modulated delay line, as I described, and I have frequency and depth controls, and I can turn on and off basically this normalization of the modulation amount by frequency. So first, we'll start with it off, and you can hear what it sounds like. So, nice chorus, right? Sounds all right. I turn up the frequency. It's more detuned. This is even more pronounced if I turn up the depth more. It sounds more out of tune. It's not nice. If I turn on the compensation, so now I have a consistent amount of chorusing. You see now the pitch is staying the same, and I'm really just manipulating the time-dependent part. So in this way, like I can just dial in the amount of chorusing that I want and change how often it repeats, which are really, those are in the end the things that semantically you want to control about the sound. You don't want to have this complex dependence. So yeah, simple change, but already a good win there, I would say. Okay, 15 minutes left. Yeah, so the final kind of point on parameterization is that, I mean, this is related to the number of parameters that I was talking about before, but also thinking about ranges. So really don't be afraid to restrict parameters for aesthetic reasons. It's okay to make choices, in my opinion. Like, it's very, very tempting when you're making a device to offer wide ranges, because you think, oh, well, maybe somebody will find something interesting in this range. Like, I don't want to stop them doing that. But this is kind of like, most of the time this doesn't work. Often you'll just end up with large areas where people can't find anything that they like. So I think it's always good to remember that as the designer, you can make aesthetic choices. That's perfectly valid, and you should do that, because you're doing some of the work for the user then. You're making it easier for them. You're giving them a better experience. OK, so that's parameterization. The last and kind of most esoteric kind of section is, well, I'm calling it secret sauce / magic. So stuff that you can add into an algorithm that, I don't know, just makes it better, makes it more interesting, makes it surprise people. So like I said back at the start of the talk, when you're making something for artistic use, it's really, really great if you can give the user like surprises and happy accidents, because you want it to feel like the user is basically collaborating with the device. Like it's something that they can bounce off, rather than it just being a tool that does exactly what they want and nothing else. I mean, there is, of course, space in the world of music production for well-behaved tools, but a lot of the time, maybe you want it to be a bit more creative. So in this direction, I would say that sometimes some amount of mystery is a good thing. So it's OK if you obfuscate the workings of a device, or give parameters a slightly unusual name, or, I don't know, just don't reveal all of the operation. Let people fill some things in their mind and imagine what's going on. It makes it feel a bit more special. Like, the human mind's a really powerful thing. So if you give people a space in which to fill in some gaps, then they'll probably fill it with interesting things. Maybe more interesting than what is actually going on in there. I mean, people do this all the time in the audiophile realm. Like, you might have a box with like a capacitor and a resistor in it, but people will say that it does all kinds of magical stuff to their audio. Because, yeah. And I mean, that's a bit of an exploitative, that's at the exploitative end of the scale, but you can also use a similar kind of approach for good, to make people more inspired and make them enjoy working with your device. Yeah, and I would also say, like, even if you're not working with a virtual analog model, then it's nice to learn some of the lessons of analog gear. So it's always good to add in some small amount of unpredictability, noise, randomness, movement, or even, actually, this is something we've only experimented with recently, but it's really cool, like parameter hysteresis. So it's really interesting if you have a parameter that arrives at slightly different values depending on which direction you're approaching a point. Like, you can really then make the space which the person is navigating more complicated. And it's pretty easy to add effects like this into particular nonlinear systems. It can be cool. So if you add little touches of all this stuff, then it tends to give the end result, in my opinion, more life. Like it makes up the gap between something that's static and boring and something that feels like it's living a little bit. Okay, so the second, I don't know why I put a picture of Aleister Crowley here. It seemed appropriate at the time. The second aspect of the secret sauce is it's about use cases. So, I mean, this is especially true if devices are more on the building block level, like you would get in a modular synth rather than a complete device, or even on the level of a pedal, maybe. Like, I think it's really, really great to think of ways that people could use your device that aren't what you would expect them to do. Like, often people find ways of using things that are not the way that they're intended originally, but they sound great and they do something really cool. So sometimes it's really interesting to try and kind of think ahead of people, like try and find something that like kind of out of the way of the normal use case that is cool, and then tune to make it sound good. So like if somebody finds this misuse, then it's going to be good already. You will have thought about it and kind of anticipated them a little bit. I mean, you can do this in all kinds of different ways. Like a really great example is perhaps with, I mean, a lot of people do this with filters in modular synths. You can very easily make a filter that also does interesting things to control signals. Like, for example, the basic state variable filter can be a great modulation source, like if you turn it to a really, really low cutoff. It can also be used for synthesis, like if you have an almost self-oscillation setting, and then you send an impulse to the input, it can ping. Like if you think about these use cases ahead of time and kind of try and make them easier and make them sound good, then it kind of gives your device more depth. I don't know, personally I find this really cool. If I have a device and then I'm like messing around with it, trying to explore the outer regions of it, and then I find something that does, which is I didn't expect, but it works really well, then that I always feel very pleased and kind of grateful that the designer has, well, sometimes put that in there to be found, or sometimes it's random, I guess, but whatever. It's nice to build that in there sometimes. Okay, so that was basically the end of my list of rules. I hope it wasn't too trivial for everybody. I think, I mean, a lot of this stuff seems trivial if you've worked on making things for a creative end use, which I guess a lot of the people in the room have. But personally, I know that when I started doing this stuff, I didn't know this. And I didn't have a web page or a book I could go to look up and find this stuff. So I was hoping to kind of bridge that gap a little bit today. I was going to finish off now by presenting a few inspiring designs and designers and saying like why I like what they do. I also had some product kind of case studies, but I think we're probably not going to have time for them, unfortunately. But if you're interested, we can go through them like in the poster room or in the during coffee time at some point in the next week or whatever. So, inspiring designs, basically giving shout-outs to people I think are cool. First one is Don Buchla, who sadly died recently. In a way, I think he's kind of like the master of designing musical devices, like one of the best people that we've had in this area over the last 50 years. And that's because he strikes this incredibly interesting balance between giving people like a really wide area of sound to explore, but also have each control do something really, really easily understandable and like obvious in a way. Like if you play with one of his instruments and just turn a particular knob, you know exactly what it's doing to the sound immediately, even if you don't know what's going on under the hood. And often it's parameterized in a way that it's very hard to do something wrong. Like you can do whatever and it still sounds great. And that's a very valuable thing. That makes a great instrument. I'd say he's also the master of, was the master of exploiting kind of quirks of the underlying technology. So a really good example of that is the low-pass gate, which is a really interesting circuit. I gave a paper on it a few years ago at DAFx on a model of it. This is basically just a normal filter, kind of fundamentally like a Sallen key filter, basically, but controlled with, instead of being controlled by a transistor as the variable resistance element or a diode or whatever, it's controlled by Vactrols, which are this weird combination of a LED and a light-dependent resistor that have really weird time-dependent behavior. So, I mean, he noticed the weird behavior of this component and then designed a whole filter around it. And the end result is something that, I don't know, is very elegant in my opinion. It's a really, really simple design, and it utilizes this really natural behavior, like this kind of natural decay of a component to provide a really organic sound. So it has this natural response to control that feels great, and it on the design level it's also quite satisfying because it's not something that's been kind of engineered in there. It comes naturally from the material that he was working with, which I think is cool. So another guy who I think does amazing designs, a bit more out there, a guy called Pete Blasser in Baltimore. He has a number of different brands under which he releases instruments. His main one is called Seat Lombard, but he also makes modular modules and other kinds of smaller instruments. Basically, he's a great example of what happens if you take the secret sauce to an extreme. So he's invented basically an entirely new language and an entirely new set of building blocks that are unlike what other people use for building devices. And he has his own names for them, his own names for the behaviors, and his own paradigms for working with this stuff. So it's very, very kind of unusual, but still completely self-consistent. And this makes it a very interesting kind of and rewarding set of instruments to work with, because as you learn the language, then you discover all kinds of possibilities that thinking in the normal way would not have led you to. And for me, this makes it, or his designs, very inspirational. The last person I wanted to give a shout out to was Tony Rolando from Make Noise Music, and also Tom Erb, who's worked a lot with Tony, but also teaches at, I think, UC San Diego. They make a lot of modular modules, and also basically standalone devices these days. Some of them are very much in the tradition of Buchla, so they pick up where he started and kind of take it further. But recently they've been doing some very, very interesting stuff with DSP, which I find very inspiring again. So they've taken this idea of an effects processor as being like a static thing at the end of your signal chain and then thrown it out the window. So they've taken standard kind of effects processors and then designed them to be playable, designed them to respond to different controls in a very interesting and creative way. And then the especially cool thing for me is that then they provide these processors with a way of interacting with the rest of your musical system. So giving control back out and creating this kind of bi-directional relationship with other processors. Like, I think this is a really interesting design direction for the future, because like this kind of traditional model of a stack of processing elements that happen one after the other and don't really talk to each other, that can only go so far. So allowing your different instruments, your different devices to talk to each other and do interesting things based on what each other are doing, I think that's a pretty interesting avenue to go down. Okay, so we're pretty much out of time. As I said, I have some product case studies. I can talk about them with you individually if you're interested. That's just a kind of overview of some recent things I made with NI and how these principles were applied in designing them. But apart from that, I guess that's it. I'm done.
Well, Julian, thank you for taking us backstage. Let's see who followed you there and still has some questions. One question here.
In an age where the typical workplace for a sound designer is sitting at their laptop, probably not even in a studio, why are we still using knobs in user interfaces?
Because it's the most compact target, I guess. I mean, basically any control on a GUI is kind of the same. Like you drag in a certain direction and it makes something bigger or smaller. I mean, if you have a slider on screen, basically the interaction is the same. It's just displayed in a linear manner instead of a rotary manner. Like we don't actually physically turn knobs on a screen. So yeah, I've thought about this before because it is a bit frustrating just seeing knobs everywhere. But yeah, my conclusion is basically just that this is the most compact way to represent the information, and it's like an easy, obvious thing for somebody to click on and change. Like it makes sense, right? Of course, more kind of dynamic graphical representations of things are an avenue that people should go down, I would say, in these designs in the future, but that's probably the reason for the status quo at least. Thanks.
When designing small modules versus designing like maybe like a complete synthesizer, so do you take different approaches to the design, or you still will design a complex instrument as a sum of modules?
I'd say if you're designing something to stand alone as a small module, you need to think a lot more about how it plays with the outside world. Like if you're designing a filter to sit in the middle of a synth, then you basically know how people are going to manipulate it because you're providing the means for them to do that. Whereas if it's part of a modular synth system or something, then you have to try and anticipate other ways of it being manipulated that you maybe wouldn't have thought of straight away. It's basically just, yeah, you need to provide, you need to think about a wider range of uses. So yeah, I would say it's quite a different process. And I don't know, rewarding in different ways actually, because the end result is different. When you're designing a modular synth module, then it's something that has to live in kind of an ecosystem with other stuff, whereas a complete synthesizer is just monolithic, yeah. But still can be very interesting, yeah.
How do you deal with, you were talking about parameter compensation.
Yeah.
When I'm designing instruments, I often find it's difficult to decide when to compensate for a parameter and when not, because usually users have experienced non-compensated parameters and have an expectation. Like
that's true, yeah.
With a delay, you could compensate the feedback so that you have a constant RT60. But people are so used to turning up the time and getting a longer tail.
Yeah. Yeah, that's true. I've experimented with the same thing, actually, RT60 on delays before, and it's true that in the end, probably you don't want to do it because people are too confused. I mean, generally, my approach would be work out what the perfect compensation is, like on paper, do the maths, and then dial it back so that you're just compensating a bit, and then you'll have, basically then you can please both sets of people, so the people who would prefer a perfectly compensated thing and also the people who are used to some other behavior. Like if you put it somewhere in the middle, then hopefully you can hit both cases. That's basically how I do it. Have we got time for one more? Or? Yeah.
Yes, one question.
I don't want you guys to miss the bus tour, so.
So for your inspiration, you've mentioned a lot of hardware instruments. Could you mention something in the software realm?
Actually, yeah. To be honest, I had some other slides about software, but then I realized the people that wrote them were going to be here, and it seemed a bit, I don't know. I didn't want to be too political about who I was giving shout-outs to. So there's definitely really great software out there that's designed very well. Maybe I can tell you later in the pub.
Okay, I think this was a good final answer. Since the buses are already waiting and the people are leaving, let's thank Julian again and close the session.